Hello everyone. In this lecture, we are going to discuss about the Turing machine introduction. Alan Turing invented the Turing machine. He invented the Turing machine as a tool for studying the computability of the mathematical functions. So a Turing machine can solve any problem that a modern computer program can solve. The Turing machine has finite control and a infinite tape. Finite control may be in any one of the finite number of states. It is similar to other automatas. And tape. The Turing machine has a two-way infinite tape. It is infinite to both the left end as well as right end. So this tape is divided into cells or squares, and each cell can have finite number of symbols, any one of the finite number of symbols. So the cell can have input symbol or blank. The input string can be placed on the tape and the rest of the cells can hold blank symbols. Blank is a special tape symbol. So initially if we want to check whether a string is accepted by the Turing machine, means first we need to load the string on the tape, and the cells that are in the left side as well as right side all will hold blank symbols. And the tape has a tape head also. The tape head is always positioned at any one of the tape cells. Initially it is scanning the leftmost symbol of the input string. So in this example we have loaded x1 x2 up to xn. This is the input string. So the tape head is initially scanning the first symbol of the input string, that is x1, and the tape head can either move on to the left side or right side. So the Turing machine has 7-tuple notation. So the Turing machine M is equal to Q sigma gamma delta Q naught BF, where M is the name of the Turing machine. Q means it's a finite set of states, sigma finite set of input symbols, gamma set of tape symbols, and the input symbol is always the subset of tape symbols, and delta is a transition function. It takes 2 arguments as input and 3 as the output. So del of q comma x is equal to p comma y comma d. The meaning is the Turing machine is in current state q. Now the state of the Turing machine is q, and the tape cell has x. That is, the tape head is scanning the tape cell tape symbol x. X is the current tape symbol. Q is the current state. So in one move, the Turing machine performs 3 operations. That is, the current state is changed to the next state P. Current state Q is changed to next state P. Sometimes it may be same as the previous state. So this state may be equivalent to Q sometimes. So this is the first operation. It changes the current state to next state. Then the tape symbol X is replaced by Y, another tape symbol, and this tape symbol may also be same as the previous tape symbol. Then the third one is direction of the tape head. So D represents direction of the tape head. After performing this operation, if the tape head is so the D may be either L or R. If the direction is L, then the tape head will move to the left side. If it is R, then the tape head moves to right side. Then Q naught is a start state, B is a blank symbol, and F set of final or accepting states. The next one is instantaneous descriptions for Turing machines. We use a string to represent instantaneous descriptions. So here x1, x2, dot 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 up to xi I minus 1, q xi plus 1, dot 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 up to xn. And here the current state of the Turing machine is q, and it is written before xi. The meaning is tape head is now scanning xi. the ith symbol from the left end. Okay, so Q is the current state and XI is the current tape symbol. And to represent the instantaneous description or move of the Turing machine, we need to use the turnstile notation. It represents move in one step, and star, if we place star above this turnstile notation, it represents moves in 0 or more steps. So del of q comma xi is equal to p comma y comma l. If this is the case, if we are in the current state q and xi is a current tape symbol, and means this is the transition function. So what about the move in instantaneous description? What about the move or instantaneous description? So x1, x2 dot 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 up to xi minus 1, q xi plus 1 dot 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 up to xn. So q is the present state and xi is the symbol currently scanned by the tape head. Means then we need to change our state to next state p. Q should be changed to p. This xi must be replaced by y and move is left move. Okay, so we need to write x1, x2 dot 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 up to, if the tape head is moving left side, means it should scan xi minus 1, right? The tape head now should scan xi minus 1. So what about the previous symbol xi minus 2? Xi minus 2, and then we need to write the state, but instead of q we have to write p, because q is changed to p in this transition function. So xi minus 2 p. After writing the state p, we need to write this symbol, right? Because left move means the tape head is now scanning xi minus 1. So the previous symbol is xi minus 2. Instead of instead of q we need to write p, then xi minus 1, and then we have to write xi, but instead of xi we have to write y. So y, then the remaining symbols xi plus 1, xi plus 2 dot 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 up to xn. This is the instantaneous description for the left move. Then we need to know about right move. So del of q comma xi is equal to p comma y comma right move. Means then x1, x2 dot 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 up to xi minus 1, q xi, xi plus 1, xn. Means now the tape head is scanning ith symbol xi, okay, but right move means it has to scan xi plus 1. So we have to write x1, x2 up to xi minus 1, no change up to this symbol, these symbols. Then we have to write xi, right, because tape head now should scan xi plus 1. So after writing xi minus 1, we need to write xi, but instead of xi we have to write y. So the symbol is tape symbol is replaced by y. Then we need to write the state, but instead of q we have to write p. So p, then xi plus 1 dot 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 up to xn. So this is the instantaneous description. Then the language of a Turing machine. So let m is equal to q sigma gamma delta q naught b f be a Turing machine. Then the language of the Turing machine is represented by L of m is equal to, the language has set of strings w in sigma star, set of strings w chosen from the input alphabet such that the condition is q naught w, where q naught is a start state, right? So q naught and w, it means that if we start checking the instantaneous description q naught w in some number of moves, if we have got this configuration alpha p beta, where alpha and beta are the tape strings, any tape tape symbols, and p is a final state. Okay, so if we have to start finding the moves, instantaneous descriptions for Q naught, the start state, and this W. In some number of moves, finally we have to reach the final state. The alpha and beta may be any tape string, it may be anything, but we have to reach the final state. So if we reach the final state, then we can say that W belongs to this particular language. And these languages are called as recursively enumerable languages. That means languages recognized by Turing machines are called as recursively enumerable languages. Consider one example. We have to construct a Turing machine for the function f of x equals x plus 1. That means an increment operation. So, if the tape head initially has 3 zeros, for example, here input alphabet is not given, sigma is not given. So we can take any input symbol. It may be 0, 1, A, B, anything. Okay. So I'm going to take zeros as the input symbols. So if the the tape initially has 3 zeros followed by some blanks. Okay. The rest of the tape cells will hold blank, and the tape head initially scanning the leftmost symbol of the input string, right? So initially if the tape has 3 zeros, then it should contain 4 zeros at the end, right? We are going to perform increment operation. So 1 is added, f of 3 symbols means then it should become 4 at the end. So how can we achieve this with the help of Turing machine? Initially the tape head is scanning 0, the first symbol of the input string, right? So if the zeros are the input symbols, then we should keep on move on to the right side until we reach blank. So whenever we reach blank, it should be replaced by 0, and then we can enter into the final state, right? So initially we are scanning 0, so no change in 0. Then tape head should move on to the right side. Then the next symbol is also 0, so no change in 0. Then it should move to the next symbol. It is also 0, so no change in 0. Next, the tape head is scanning blank. Now this blank should be replaced by 0, and then we can enter into the final state. So now the tape has 4 zeros. So suppose if initially the tape has 5 zeros, finally it should contain 6 zeros. This is our aim. Okay, so we can construct the Turing machine table for the Turing machine construction. Here rows correspond to the states, columns correspond to the tape symbols. Okay, so here we need 0 and blanks are the tape symbols. So 0 and blank, and assume that Q naught is a initial state of the Turing machine. So whenever we are in state Q naught and zeros are the tape symbols, then just we have to perform right move, right? No change in state and no change in tape symbol. If we want to perform some repeated operation, some loop or repeated operation, then don't change the state, then only it will perform repeated step. Otherwise we have to write for every new symbol. It is not possible for the general case. So if we are in state Q naught and tape symbol 0, no change in state and no change in tape symbol, just move right side. Okay, so 0 is the current symbol, tape symbol, and Q naught is the current state, means then no change in tape symbol, no change in state. Just we need to move on to the next symbol. Okay, so now again the tape symbol is 0. So Q naught and 0, the state is also Q naught, no change in state. So Q naught 0. So Q naught remains Q naught, 0 remains 0, move is right move. So this is repeatedly performed until we reach blank. So we will see blank at one point of time. So in state Q naught, if blank is the next symbol, then we need to change our state to next state Q1. Then blank must be replaced by 0. Move is either left or right move because our aim is to replace one blank symbol by 0. So the next move is either left or right move. And here definitely we need to change our state to next state, because if you don't change the state, then q naught blank becomes q naught. The meaning is it will enter into the infinite loop and continuously it will keep on replace all blank by 0. So if we want to do one operation, one symbol change, means definitely we need to change our state to next state. If we want to do something continuously, means don't change our state. Okay, so here we need to change blank by 0. So change state to q1. q0 to q1, blank is replaced by 0 and the move is right move. So what is q1? Now q1 is a final state. There is no operation for 0 and blank. So this is the transition table for Turing machine. So now we can write the 7-tuple notation. So Turing machine M is equal to a set of states. So what are the states here? q0, q1, and set of input symbols. Here the input symbol is 0 and set of tape symbols 0 and blank. Then delta is a transition function that we have written as a table. So delta, it may also be written as a list of transition functions, and diagram also, transition diagram. We can represent delta in any way. So delta, then start state q naught, blank is the special tape symbol, then the final state is q1. It should be represented within a brace, set braces. Okay, so now we can see how to draw the transition diagram for this same problem. So the transition diagram means it's a graph like representation. So it has states and nodes and edges. So states correspond to nodes and edges must be labeled by the transition functions, and start state is indicated by the word start and an arrow leading to that state. Final states are indicated by double circle. So in this example we need two states, q0 and q1, and q0 is a start state, right? So it should be represented by arrow and the word start. Okay, then from q0 to q0 there is a transition. So suppose if there is a transition like this, q comma x equals p comma y comma right move, means from state q to p we need to draw an edge, and this edge must be labeled by x forward slash y. Right move means we need to put a right arrow. If it is left L, then we have to draw the left move. Okay, left arrow. So from Q to P, draw an edge, and that edge must be labeled by X forward slash Y right move. Okay, so similarly, Q0 to Q0, we have to draw a transition. So from Q0 to Q0, transition is, this edge is labeled by 0 slash 0 right move. Then from Q0 to Q1, and Q1 is a final state, so it is represented by double circle, and from Q0 to Q1 draw an edge, and that edge is labeled by blank slash 0 right move. Okay, so this is the transition diagram representation of the same problem. Now we can take one example string and check the instantaneous description. Okay, so whether it is converted, we have performed the increment operation or not. So assume that we have the string 000. Okay, 000 is a input string. So finally our tape should contain 4 zeros, right? So 000 means, so we have to check the q0 w, right? Q0 is a start state, and W in some number of moves finally we have to reach the final state. So here the start state is Q0, Q0 0, Q0 and 0 means the move is right move. So right move means we have to write the state after this 0, right? So leave one space for 0. leave one space for this symbol. Now we need to write the state. And what about the state? No change in state, Q naught. Now we have to write 0. And this tape symbol 0, no change. Okay, no change in 0. This is not replaced by a new symbol. So 0 should be written as 0. Now write the remaining symbols. So 0, 0. And the next symbol is obviously a blank, right? So next, Q naught and 0. Again the same transition. So Q naught and 0. Move is right move. So we have to write the state here. And what about the number of state number? Q naught. No change in state. And no change in tape symbol. So this 0 should be written as it is. Write the remaining symbols. Then Q naught 0. Q naught 0. Again the same transition. Move is right move. State Q naught. This 0 is replaced by 0. Okay, so first we have to write about check the move, whether it is left move or right move. So we have to write state here. And what about the state? Q naught. And what about the tape symbol 0? This tape symbol 0, no change in tape symbol, that is written here. Then write the remaining symbols. So 0, 0, blank. Then Q naught and blank. So what is Q naught and blank? Move is right move and state becomes Q1. This blank is replaced by 0. Now write the remaining symbols. And the next symbol is also blank only. Okay, because all the tape symbols infinite to the right side as well as left side will hold blank. So Q1 blank. Now what is the transition for Q1 and blank? It is undefined, right? So Q1 is a final state. Q1 is final state. So Q1 is a final state. And Q1 comma B is undefined, right? We don't have any transition here, undefined. Therefore, the Turing machine halts as well as since Q1 is a final state, it accepts this input string. So what about the input? Initially it has, the tape has 3 zeros, finally it has 4 zeros. So it enters into the final state. That we can write it as it accepts the input string. But in this problem, the Turing machine is used as a computing device. Okay, the Turing machine can be used in two ways. The Turing machine can be used as a acceptor or transducer. Transducer or computing device means from the input, output can be generated. So here it performs the incrementation operation. Similarly, we can make our Turing machine to perform decrement operation, addition, subtraction, multiplication, any computability function. So in that case, the Turing machine is called as, Turing machine is used as computing device or transducer. And suppose if we want to check whether the string has even number of zeros, odd number of ones, 0 to the power n, 1 to the power n, palindrome, these problems are called as Turing machines as acceptor, because we will check whether the Turing machine has n number of zeros followed by n number of ones or not, right? It is not going to generate an output. So in this case, the Turing machine is called as acceptor, but in this type of functions, the Turing machines are called as transducer or computing device. So instead of writing accepting the input string, we can write it generates the output. Thank you.